Gated recurrent unit, GRU, is the first solution to the problem of exploding hidden state we have seen. It consists in specifying a relation between the forget gate and the writing gate. By letting the forget gate being equal to 1 minus the writing gate, we obtain the following equation. Now, HT is a weighted sum of the previous hidden state and the candidate hidden state. Since they are all bounded between -1 and 1, since they result from the application of the hyperbolic tangent, the new hidden state is also bounded and cannot explode anymore. Here are the equations of the GRU, together with a seminal paper at the top and a scheme of the connectivities between the different elements. The equations are the same as before, using the sigmoid for the update forget gate and the reset read gate. Here, the notation has been changed to match that of the original paper. The forget gate Ft has been replaced by the update gate Zt, but the equations remain the same. You can take some time to look at the scheme if it helps you. Another solution to the exploding problem we have seen before has been found in the above paper published in 1997. This solution is called LSTM and is very simple. It consists in applying a bounded function, here the hyperbolic tangent, to the hidden state in order to bound its values. This is shown in the last equation, where the hidden state is given by the output gate OT times the hyperbolic tangent applied to the cell state CT. Since the output gate and the hyperbolic tangent are bounded, the hidden state is also bounded and cannot explode. The novelty of LSTM is to introduce a cell state which is given by a combination between the previous cell state CT-1 and a candidate hidden state GT. This equation, the penultimate equation, resembles the fundamental equation of GRU and LSTM we have seen before. Note that the cell state can be copied to the next cell state thanks to the forget gate. This is close to the idea of a shortcut connection. The quantity CT can be propagated through the network without passing through any saturated function. This can improve the gradient flow. Here is a short comparison between LSTM and GRU. Recall that the traditional recurrent unit always replaces the activation or the content of a unit with a new value computed from the current input and the previous hidden state. However, both LSTM and GRU keep the existing content and add the new content on top of it, which helps the network to remember long-term dependencies. It is thus easy for each unit to remember the existence of a specific feature in the input stream for a long sequence of steps. Any important feature decided by either the forget gate of the LSTM unit or the update gate of the GRU will not be overwritten, but can be maintained as it is. So it's easier for the network to remember information that have been created or seen at the beginning of the sequence. It also creates shortcut paths that bypass multiple temporal steps. These shortcuts allow the error to be backpropagated easily with less vanishing effects. From an empirical point of view, GRU and LSTM performances are comparable and usually better than that of standard RNN. However, there is no clear consensus between GRU and LSTM. For LSTM, we have seen that the hyperbolic tangent plays a very important role, and the forget gate is also important since it allows the network to copy the previous cell state to the next one. Don't hesitate to look at this paper I mentioned before to get more information on LSTM.